Welcome to my channel. Today, the session. Let us discuss about the curl and the Stokes theorem. Okay. So, initially let us define the curl. Curl of the field A vector is an axial or the rotational vector whose magnitude is maximum circulation of A per unit area as the area tends to 0 and whose direction is normal direction of the area when the area is oriented to make the circulation maximum. Okay, so this is the definition. What the curl of the vector says is, if there is a vector A, from the vector A, the maximum circulation of the flux will be an nothing but which will be the rotational in moment. That means if this is the vector field and in which the electric field flux rotates along this field. Okay, so it is a rotational vector whose magnitude is maximum circulation of A per unit area, right? And the direction will be in the direction normal direction of the area when the area is oriented to make the circulation maximum. So this rotational circulation will be maximum. When it is maximum, its direction will be the normal direction of the area, right? The curl can be defined by the expression curl A, which is equal to del cross A, which is equal to the limit del s tends to 0 integral. This is the definite integral of this surface in which we are going to take a line A dot dl divided by del s into the normal vector an. So this will be the maximum when the circulation is maximum. Okay, so curl is defined by the formula curl A, which is equal to del cross A limit del s tends to 0 integral L A dot dl del s maximum into A vector. Simply speaking, curl can be defined as the surface integral is equal to the line integral. So this definition is extended towards the Stokes theorem. Whenever del S is bounded by the curve L, this is the surface area of the electric field which we have taken. So, and An is the unit normal vector of the surface. To obtain the expression of del cross N, we are going to take a differential area plane which it has the two coordinate axes. It is defined by y and z. Okay, in this we have taken a small elemental area dy and dz. So this is the closed path and also this is the linear path. While taking the line integral for this surface A, B, C, D and A, this surface which is extended by the Taylor series expansion and having the center nothing but x0, y0, z0. Okay, so while expanding by the means of line integral AB A dot dl, we have taken the two components y component and z component. The y component and z component are with the center of axis y0 and z0. We have neglected the x component since we have taken only the closed loop path, rectangular path. Okay, on the side of AB, the small element dl is given by dy into ay and the center is given by z axis is given by z0 minus dz by 2. So this shows that the flux is away from the center. Okay, so, while integrating along the A line AB, we get the expression in such a manner, and along BC, we get the expression in such a manner. So we have taken the point center point as P, since we are mentioning the integral equation as P. Similarly, we have seen the two sides, that is A and B side. And next, we have to see about the CD and DA. Okay. So if this is the component, we have seen the two sides AB and BC. We need to see CD and E. Right. So these two are in the positive direction and the other two they are in the negative direction, minus dy and minus dx. From this, we get the curl expression as nothing but, while substituting all the expressions, we have taken del s as dy and dz. Since we have only two components, we have neglected the dx. Okay. And the curl of the expression for x, y, and z components can be written as dou a z by dou y minus dou a y by dou z. And similarly for y and x component, we have written as in such a. And finally, we get the curl expression as, in case of the Cartesian coordinate, this is the curl expression del cross A. For obtaining this expression, we have defined the curl of the vector. Curl of the vector is, while operating the curl of the vector, we get the vector component only. And we have defined that if there is a electric field flux, the flux will be rotating along the ring. So in the closed path, by the closed path, we have defined the curl of the vector del cross K. And this is given in the Cartesian coordinate. Similarly, if we write the expression in the cylindrical coordinate, we have the expression as del cross A is equal to 1 by rho. So the xy z terms are represented by rho, pi and z. So our expression will be del cross A is equal to 1 by rho into a rho, rho, dou rho, etc. And this, if we write in the case of spherical coordinate, we have written in the case of the cylindrical coordinate. If you write the same expression in the case of spherical coordinate, the del cross A vector in spherical coordinate is written as del cross A, which is equal to 1 by r is to the cos of r, theta and phi. So in case of spherical coordinate, it has the coordinates r, theta and phi. We have represented this spherical coordinate in this manner. Okay. So we have started with the definition of curl, and we have written the expression for del cross A in terms of x, y, z, and similarly in the case of cylindrical and the spherical coordinate. Simply speaking, curl of the vector is nothing but the surface integral equal to the line integral. And for obtaining the surface integral, which is equivalent to the line integral, we have taken a vector field and we have considered that the flux is rotating along the axis which we have taken. That is, and the flux is also maximum in the closed path of circulation, right? And the main property of the curl is nothing but, if you operate the curl of the vector, we will get only the vector field, right? And similarly, divergence of the curl field vanishes when del dot del cross A is equal to 0. This is an important property in the case of curl. And similarly, curl of the gradient field vanishes when del cross del V vector, which is equal to 0. This is another property of the curl. While discussing about the divergence vector, we have said if we operate the divergence, we will get another scalar field. The divergence, curl, and the gradient of the scalar are given by the means of the operator, del operator. Right? What is del expression? Del expression is nothing but dou by dou x into ax plus dou by dou y into ay plus dou by dou z into az. These expressions have already discussed, right? And now, the curl of the vector when it is applied to the Stokes theorem. By the definition, the Stokes theorem is given by integral L A dot dl, the vector A into the small element dl, which is equal to the surface integral of del cross A into ds. This is called the Stokes theorem. So consider the surface in this. Take a small elemental area ds This is the closed surface. I am taking the line integral, and the Stokes theorem states that the circulation of the vector field A around a closed path L is equal to the surface integral of the curl of a vector A over a surface bounded by L, provide that A and del cross A are the continuous. The vector field and its curl field are continuous on the surface, which electrical field surface which we have taken, right? So once again, for this we needs to have a proof. The proof is similar to that in the case of divergence theorem. We have taken a surface, we are going to subdivide the surface as discussed earlier. If we subdivide this area is divided into the multiple cells. In these multiple cells have fluxes. The flux incoming and the outgoing cancels together. Finally, we get the same expression as integral L dot dl, which is equal to sigma k integral L k A dot dl. So the Stokes theorem is nothing but definite integral line integral of vector A dot dl is equal to the surface integral del cross A into ds, which is nothing but the Stokes theorem. Okay, and we have started our discussion from curl of the vector, and finally we have extended the curl vector expression towards this Stokes theorem. Stokes theorem is nothing but the application of curl of the vector. Simply speaking, the curl of the vector, when it will be operated, it will provide only the vector output, and the main property of the vector is nothing but divergence of the curl field vanishes, and also the curl of the gradient also, the field also vanishes. If you like this video, like, share and subscribe. Thank you.